You're listening to the Good Question Podcast with Richard Jacobs. Our goal is to make each of our guests exclaim, that's a good question. I don't know the answer. Because when that happens, it means you, the listener, may be inspired to learn more beyond the interview and to ask great questions yourself that lead to new insights. In this podcast, we cover historical and current anthropology, comparative religion, and history. Welcome, and let's get started.
Hello, this is Richard Jacobs with the Good Question Podcast. My guest today is Tyler Korman. He's a Chief Scientific Officer and co-founder of eXoZymes. It looks like they've innovated an entirely new method of making chemicals by taking enzymes, which are molecular workers inside cells, and coaxing and engineering them to operate outside a cell. So this is going to allow them to make some really interesting structures and chemicals for biological applications. So welcome, Tyler. Thanks for coming.
Yeah, thanks for having me.
Yeah, I'm sure you can express it better. What's the underlying premise of eXoZymes? Did I capture it right, or is there some more nuance to it?
You did a great job, actually. That's the general premise. When you think about how biology works, really, the things that allow you to eat food and convert it into energy, that's all catalyzed by enzymes. So these amazing catalysts that function to break things down and build chemicals up to, make energy, use energy, all that kind of stuff. And so this process happens not just in humans, but in plants, bacteria, all kinds of living organisms. And this has been harnessed by people in the biomanufacturing industry to say, hey, we can use these properties of these enzymes to actually re-engineer organisms to make the stuff, other things that we actually might want that contributes to the economy. And so it's great in principle, but turns out it doesn't often work all that well. But that being said, the catalysts, these enzymes are fantastic. They do work really well. And so we had this aha moment. We said, what if we just got rid of all these complexities of, the living organism around it, isolated those enzyme catalysts and put them back in a pot and said, hey, what can we use them to make? And so that was the general premise. And so far, so good. It works quite well.
And how do you prepare the enzymes in bulk? Can you just create them through regular organic chemistry, or do you have to culture a bunch of cells and then grind them up and strip out the enzymes? How do you get to them in mass?
Yeah, you still have to use organisms, microbes, either some type of bacteria or yeast to make them, but that's something that works really well. I mean, you look at how you use enzymes every day and you don't even probably realize it. They're in your laundry detergent, they're in your dishwashing detergent, they're in some of the products you use. And so enzymes are already produced at very, very large industrial scales. It's a technology that works, and organisms really like making enzymes. What they don't like making are these chemicals that could be toxic. They could kill the cells. And so we said, well, let's let the organisms make what they want to make is enzymes, and then isolate them and then make those chemicals in a separate pot.
What about the role of localized microbiome? Do enzymes really do all the job of eating food or consuming food, or how much of it is microbiome mediated? And have you seen in your attempts to make compounds that there's missing links that possibly could be filled by that, or what's the story?
Yeah, so I mean, when you think of the human body, it's really a system, right? It's not just your human cells, but there's, like you said, there's a microbiome, there's microbes and things that help us break down stuff. At the end of the day, all of that activity, whether it's in a bacteria or in your cells, is catalyzed by an enzyme. And so this is kind of a ubiquitous process. Sometimes those enzymes are missing in the body. Sometimes when we're thinking about a pathway that exists, say, in a plant or some microbe to make a new chemical, we might not know everything about that pathway, or it hasn't been discovered yet. And so there's processes that we can use to kind of jump some of those gaps, fill in those gaps. We can either search for those missing enzymes using all of the sequencing data that's been put together, or we can kind of design new enzymes that can fill those steps.
What kind of compounds have you been able to successfully make? What applications?
Yeah, so it really varies. And so when we first started this project when I was at UCLA doing my postdoc, and we started off funded by the Department of Energy. So we started off with fuel-like commodity chemicals. These are kind of second generation past ethanol, a molecule called isobutanol. It's toxic to microbes, so it's difficult to produce in those cells. And as we got better and better at making, using those systems, building those systems to make those types of chemicals, we expanded into more complex things. These are things like cannabinoids. These are things like terpenes that are flavor and fragrance compounds in plants. And so we've made a lot of drug-like compounds. And so that's the beauty of biology, is it can be both. It really runs the gamut from very simple, like ethanol, all the way to the very complex, like some of these drug-like molecules that are produced in plants.
I thought it would be interesting. What if you had a restaurant and you paired digestive enzyme with all the food? It came on a little plate and you ate them with dinner. And then when, by the time dessert comes, you'd be hungry and you eat some enzymes with that, like lactose or whatever it is. This would be a funny idea, maybe because you're involved in the production of enzymes, you might laugh at it.
Yeah. And I mean, enzymes are used in so many different places. There are products out there in the market that actually do that. Like I think Beano helps you digest some of those, legume-based compounds, lactate and lactose and the lactate that helps you break down the lactose. So yeah, you're not wrong. Like that's great. And there's other opportunities as well. You can also produce, there's certain molecules that help activate both your cells and the microbiome to allow you to break down, kind of your food and everything much better as well. And so there's opportunities to, maybe it's not an enzyme, maybe it's some other natural product that you kind of eat, like maybe as a supplement on a daily basis that also helps. And so, there are really a lot of opportunities in this space.
The end products you're making are not necessarily biological, but you're just using cells to make them, to make the enzymes, then to make the products you want.
Yeah, we use, biology as our inspiration. And so we use biology, living organisms to make the enzyme catalysts. And then we do what is effectively kind of those chemical reactions using those biological catalysts to make the products. And so the products that we make are small molecules, and they can be any type of compound from like a nutraceutical to a pharma. And that inspiration from biology is what's key here, because there's so much beauty and complexity in that that sometimes it's hard to get to using organic chemistry or extracting it from natural sources. So there has to be other ways to make them.
So what are the what are you making? What's in the greatest demand that your system is really good at making?
Yeah, so we're really excited about kind of one of our flagship products, NCT, N-trans-caffeotyramine. It's a compound that's present in black peppercorns and some other plants as well. You can make it using chemistry, but it tends to be very dirty. And you can extract it from plants, but it's not present at very high amounts. And this compound has been shown in the literature to really boost metabolism and to kind of help your body potentially get rid of fat. And so we're really excited about being able to actually make this compound and make it at really high levels and purities that haven't been seen before to really help people in their healthy lifestyles. And that's just one example. We have a number of other compounds that are also, important in the pharmaceutical space, where there's unmet needs for a variety of different indications, like CNS disorders and other types of metabolic disorders that can also be addressed with kind of plant natural products or derivatives of those, which kind of gives you that pharmaceutical angle.
Are enzymes usually consumed in a reaction, or do they stay, or do they get altered? Like what happens to them? Do they need to be cleared out once a reaction's done, or are they consumed?
Yeah, so I mean that's the beauty of using a catalyst, because you just need a little bit, and it allows it to you get a lot of bang for your buck, and so it allows it to cycle many times. A catalyst does, and so you need just a little bit of that catalyst, and then you can make your product. At the end, though, you do separate the enzymes away from your final product, and so what you end up, but because of the way that we're doing this, these are really clean input streams, and so you're not adding a lot of dirty inputs, there's not a lot of side reactions like in chemical reactions, and so your inputs are clean. That means your outputs are going to be clean, and it makes those final products just that much easier to isolate.
What happens to the enzymes? Are you able to reconstitute them, or are they good to go for another round? Like you don't need to produce maybe a large initial amount, but to make this commercially viable, is it?
Yeah, I mean it comes down to like a cost question, and there's a lot of different ways that you can address that challenge. I think there's a number of groups that have a couple different strategies. There's some I like better than others, but really at the end of the day, if you can use those enzymes for a longer period of time, that's similar to like recycling, like what you were suggesting, being able to reuse. And so I like that approach better right now. I think it's an open question for how much you actually have to do, because if you just need a small amount of this catalyst from a cost perspective, the economics look like they work out.
Is the catalyst an enzyme itself, or is the catalyst an exogenous compound compound, or what would they be, for example?
Yeah, the catalyst is the enzyme itself. And so, yeah.
Okay. But have you tried overloading, putting, way an abundance of enzyme and to see how it changes the reaction?
Yeah, it makes it go real fast. It does make it go really fast. And so, some of the things that we talk about is like a space-time yield, right? Like productivity, grams of product per volume per some amount of time. And so, the more product you can make in a shorter amount of time, your economics get better. You can do that by either engineering those enzymes to be faster or by using more enzyme. And so you might do that, initially. But that's also the beauty of our approach, this cell-free or eXoZyme approach, as we call it, because you really have total control over the entire reaction environment, which is different than when you're trying to use or ferment, an organism to do the whole thing all at once. So we think it's a really different approach and really useful in a lot of different cases.
Well, how close are the normal products produced by cells to what you can make with your extracellular, method?
Yeah, they're exactly the same. So the molecules that we make are, biologically derived. So the NCT that we make is 100% identical to the NCT made in the peppercorn. The beauty of it is we can make the natural product, but, in the case of some other plant natural products, you make the product that's made in the plant. But if you just change your inputs a little bit, and this again is the beauty of, our process, you have complete control. So you can vary the inputs just a little, and now you get to new analogs that, builds upon that natural diversity and allows you to go into, pharma applications and things like that, where maybe the compound from nature is kind of good, but it's not great. And so if you can just make some small modifications, it can be really good. And so we take that approach.
Okay. What kind of chemicals are the enzymes? Like what, are they like aldehydes? Are they like what kind of structures do they have?
Yeah, the enzymes are polypeptides. And so they're chains of amino acids. When you take your protein shake, if you have like whey protein or, the plant protein, wherever you get that protein from, there's not a lot real different. Like it's still a chain of amino acids. It's just how that chain is, how those amino acids are linked up and which ones they are, that governs what makes a different enzyme, right? It makes one protein different from the next. And so nature has, billions, if not trillions of different types of enzymes that do different types of things. And a lot of that is known. We've been able to, the whole genomic era where you've been able to sequence, know the DNA of all these different types of organisms. Once you know that DNA sequence, a lot of times you can then know what the actual resulting protein or enzyme sequence is. And so that's pretty much all the knowledge you need to move forward and start putting these enzyme pathways together.
What about a health application? Have you discovered any enzymes that people aren't normally aware of or they don't test for in blood panels that you see are essential to cellular operation or digestion?
Yeah, I mean, that is a possibility. It's not our focus. We're not looking for necessarily how to fill in like enzyme deficiencies. We're really looking to use enzymes as catalysts to make healthy compounds. Things that are like a supplement, like an NAD or like something that you might take over the counter like that.
Okay. Is there an ideal biological carrier, a certain kind of cell or microbe that can do, can make most of these things? It acts as a useful shell.
We typically use bacteria like E. coli or bacillus that are, safe. Sometimes we use yeast as well. Those are our preferred just because there's so much known about it. They grow pretty fast. The beauty of it is we can be agnostic. So you don't have to make every enzyme in the same host, right? So you don't have to make them all in E. coli or all in yeast. If you're trying to link all the steps together inside of a cell, which is your traditional synthetic biology approach, then they all have to work in that given organism. With our approach, you kind of uncouple that requirement. And so it leads to some efficiencies that compared to that other process.
Okay. Well, I don't know, what applications are you now considering? What's coming that's new in the next year or two, if you can say? Well, where is all this heading? I
think really broadening kind of the classes of compounds that we're trying to make, getting into other classes of compounds that can really fulfill an unmet need in the kind of health and wellness marketplace. That's one aspect. And so we have a number of targets beyond NCT and cannabinoids that we're working on. the other part of that is you take those known natural compounds that are already our targets, that have some place in the health and wellness market, and then you make modifications to make and test them for their pharmaceutical applications. And so that's another area that we're excited to move into as well.
Okay. Now that you're extracting these enzymes and again culturing them and everything, do you see any better way to make them where you don't have to use the cells at all? Can they just be made in the lab now? Again, without having to use like a biological carrier first.
We have some processes where you can leverage. It's like a cell-free protein synthesis. It kind of uses the insides of an organism. Basically, you basically make the whole extract. It's really powerful for screening, so it allows you to engineer enzymes really fast. There's a cost challenge with that approach to actually use it to make the enzymes, and so we use it a lot for screening and high throughput processes as opposed to production.
So, what's the best way for people to keep tabs on the work and to follow what's going on?
Yeah, you can go to our website, www.eXoZymes.com. We also have a pretty healthy kind of post and LinkedIn presence. There's a lot of PR. Our VP of Communications, Lasse, does a great job with pushing out content. We have our own kind of internal podcast that hopefully will be hitting the ground soon at a certain point. We've recorded some content. Really goes into kind of the history of, from a cell-free perspective, where we started and how we got onto this journey, and kind of the experience of being in a startup and going from, that academic setting to this biotech industrial complex, which is wild. It's really gone through some crazy changes over the past, 10 or 15 years. And so, yeah, there's a fair amount of information out there. Yeah, I encourage you to visit our website and find us on LinkedIn.
Okay. Well, very good, Tyler. Thanks so much for coming on the podcast and explaining all this.
Thanks for having me.
If you like this podcast, please click the link in the description to subscribe and review us on iTunes.
Thank you for listening to the Good Question Podcast. Please email support@thegoodquestionpodcast.com if you have any referrals to great guests for us to interview. Visit thegoodquestionpodcast.com to hear more interviews. And please help us spread the word by rating and reviewing us on Apple Podcasts, iTunes, Spotify, YouTube, or wherever you listen to this podcast.